It's kind of funny, right? Like we talk about all this super smart AI, these LLMs that could do amazing things, but sometimes I get this feeling, right? Maybe they're overthinking it, like taking these really long, complicated paths to get to an answer, when maybe there's a much simpler way. And then it hits me. If they're doing that, what's it costing us? Not just in like processing power and money, but in terms of real world efficiency.
Yeah, that's a really sharp observation. It's not just about getting the right answer, it's about how you get there, right? And that ties into a brand new study that's, well, it's pretty dense academic stuff, but it's asking some seriously important questions about how efficient these LLMs really are when they do what's called chain of thought reasoning.
Exactly, chain of thought. So we're diving into this paper, and the title, I'll be honest, it's a mouthful. How well do LLMs compress their own chain of thought? A token complexity approach. But stick with us because this is actually groundbreaking stuff. They're looking at whether these AI could be way more efficient, not just a little bit, but like fundamentally more efficient.
And the implications of this, they're huge. I mean, if you're thinking about the future of AI, how we're going to use it in healthcare, finance, you name it, the cost of running these things matters. And if their reasoning is inefficient, that cost goes way up. But even beyond that, just understanding how these systems think at this level of detail is fascinating in itself.
Totally. So we're mainly focused on this research paper, but also pulling in some background from our notes. The mission here is to really understand this idea of token complexity, which is key to the whole thing, and to get a grasp on what the absolute limits of efficiency might be for this kind of AI reasoning. All right, let's break this down.
So first things first, we need to talk about this chain of thought thing. As you mentioned, it's this really important technique for making LLMs better at reasoning. Back in 2022, there were these papers, Wei et al. And Kojima et al. They kind of set the stage. What they showed was that if you prompt the AI, if you tell it to show its work, like you would a student solving a math problem, you actually improve how well it performs on complex tasks.
Right, so it's like making the AI's thought process visible instead of being this black box. But here's the thing. The more detailed that process is, the more steps, the more verbose, I guess it becomes. And that starts to be a problem when you think about real world applications. It's like you and et al. Pointed out in 2024. All those steps, they add up and they become really expensive computationally.
Exactly. Each step, each piece of that reasoning chain, it costs computing power. And when you're running these models at scale, those costs become, well, significant. So naturally, people started looking for ways to make those reasoning chains shorter, more concise. Like there were these studies in 2024 by Jin et al., Renze and Gufen, Han et al. They were all experimenting with simple prompts, like literally telling the model to be concise or putting limits on how long the response could be.
It's interesting, even before this study, there was this sense that maybe these AI weren't being as efficient as they could be, like John and Lee in 2024, Wang et al. In 2023, they were already noticing redundancy in the chain of thought outputs, like the AI was saying things that weren't really needed to get to the answer.
And those observations really paved the way for this new study, which is taking a much more systematic and rigorous look at this whole trade-off between how long the reasoning is and how accurate the answer is.
So tell us about this study. How did they go about this, and what was the big overarching finding that came out of it?
Okay, so they didn't mess around. They evaluated 31, that's right, 31 different prompt-based compression strategies. We're talking about a really wide range of techniques to try to get the AI to reason more concisely. And they tested all of this on 6 different LLMs, including some of the big names like GPT-4o, Claude 3.5, and Llama 3. And to really put them to the test, they used 3 different math reasoning data sets: Math 500, a subset of GSM-8K, and a subset of MMLU Pro Math.
Wow, that's a pretty comprehensive setup. And I remember seeing in table one of the paper, they listed all these prompts they used, from just asking for the answer without any reasoning at all, they call that no-cot-T, to the standard think step by step, that's default COT, to a whole bunch designed for conciseness, like be concise, bullet points, only numbers. They even tried some pretty out there stuff like removing spaces and proper grammar, or limiting the response by words, characters, tokens, number of reasoning steps. Even tried prompting in Chinese.
Yeah, they really threw the kitchen sink at it, tried all sorts of ways to influence the length and the format of the reasoning. And here's where it gets really interesting and maybe a little surprising. They found that despite all these different prompts, there's this fundamental trade-off between the average length of the reasoning measured in tokens and the accuracy of the model. And it kind of forms a curve, which they show in figure 1. The thing is, no matter how they tried to make the reasoning more concise, the performance tended to fall along the same curve.
So it's not so much about the specific words you use to ask for brevity, but more about the overall length of the reasoning itself.
Exactly. It suggests that the length in tokens is the dominant factor, even more than the specific way the reasoning is structured, as long as it's actually informative, of course. Now, there were some nuances, like this was more apparent in the stronger models when they were working on easier tasks. And with weaker models on harder data sets, things were a little less consistent. But overall, this trend was pretty strong.
That's a pretty big insight. It's almost like for a given problem and model, there's a certain amount of information, a certain number of tokens that needs to be used during the reasoning to get the right answer. And it's the total amount that matters most, not how it's arranged.
That's a great analogy, and this leads right into what I think is the most exciting and innovative part of this study, the idea of token complexity.
Okay, this feels like the real intellectual's heart of the paper. Let's dive into this token complexity. What is it and what makes it so important?
So, in simple terms, token complexity is the minimum number of tokens an LLM needs to generate in its chain of thought to correctly answer a question. Think of it as the inherent length of the reasoning that's required for that specific problem, at least for that particular model and its training.
So it's not just a property of the problem itself, but it also depends on the specific LLM that's being used.
That's a really important point. It's not absolute, there's that dependence, but the really cool thing is how this plays out at the individual question level. They found this sharp threshold behavior. Like for a given question, across all 31 of those different prompting strategies, the LLM would usually get it right if and only if the length of its response was above a certain token count. And that token count was specific to that question.
That's amazing. So regardless of whether you ask for a short answer or let it go to detail, if the final reasoning chain was longer than that critical point, the answer was likely right, and if it was shorter, it was likely wrong. It's like there's this tipping point. And figure 2 in the paper actually shows this with an example from the MAU 500 dataset. You can really see that clear cutoff.
Exactly. And this observation led them to formally propose what they call the token complexity hypothesis. Basically, it says that for a given question, an LLM, there's this token complexity threshold. If the generated reasoning is at least that long, the answer is correct, and if it's shorter, it's incorrect. Of course, this assumes the reasoning is actually meaningful. You can't just add random tokens and expect it to work miracles.
Right. It's about the tokens that are actually contributing to the thinking process. So how well does this whole idea of token complexity hold up in practice? Is it just a theory, or does it actually have predictive power?
Well, the results are pretty impressive. They found that token complexity alone could predict how well different chain of thought prompting strategies would perform, and the accuracy was around 95%. That's huge. They even show this visually in figure 2, right panel, where you can see the strong correlation between the actual accuracy and the predicted accuracy based just on whether the response length was above the estimated token complexity. And then in table 4, they give the average classification accuracy across all the models and benchmarks, and it's consistently really high.
So it's not just a so-so predictor, it's remarkably accurate. This really points to token complexity being a fundamental measure of how difficult a reasoning task is for a given LLM, almost regardless of how you prompt it.
Exactly. It gives you this intrinsic measure of difficulty that isn't tied to any particular prompting format. Harder problems, it seems, just inherently require more thought, more tokens to solve reliably.
Okay, so we got this concept of token complexity, and it's clearly a powerful tool. Now, where do our current AI reasoning methods stand when we compare them to what might be theoretically possible in terms of efficiency?
This is where they get really into the weeds, using information theory, specifically this thing called rate distortion theory, to figure out the theoretical limits of this accuracy compression trade-off. It's a way to understand how much you can compress information, in this case the reasoning process, while still maintaining a certain level of quality, which here is the accuracy of the answer. They define all these concepts like the best possible performance you can get for a given token budget and the minimum number of tokens needed to reach a specific target accuracy.
Sounds like some serious math. So what did they find when they compared our current prompting strategies to these theoretical limits?
Well, it turns out we've got a long way to go. They found that the way we're doing things now with these prompt-based compression strategies, it's actually pretty far from those optimal limits, especially on the harder data sets like Math 500 and MMLU Pro Math. You can kind of see this in figure 1. There's this gap between the performance curves of the different prompts and what they call the oracle upper bound, which represents that theoretical limit.
So even when we're trying our best to make the AI be concise, we're still nowhere near how efficiently it could theoretically be reasoning to get the same level of accuracy.
Exactly. And this leads to something they call corollary one in the paper, which is about lossless compression, basically getting the best possible accuracy the LLM is capable of on that data set. They show theoretically that the number of tokens you need for that optimal performance is just the average of the token complexities for all the questions. And when they compared this to how many tokens the actual prompts were using, even relatively good ones like default crot T and be concise, they show this in table 3, the potential for reduction was huge. Like on MMLU Pro Math, it ranged from 3 to 11 times fewer tokens.
Wow, that's a massive difference. It really highlights how much room there is for improvement. So if we're so far from this ideal, what's the path forward? How do we bridge that gap?
Well, their study points towards something called adaptive compression. The basic idea is that the AI should adjust how long its reasoning is based on how difficult the problem seems to be. So, shorter reasoning for easy questions and longer, more detailed reasoning only when it's really needed. Ideally, it would match that inherent token complexity.
Makes sense, right? Like we wouldn't spend forever explaining something that's super obvious. Do LLMs do this at all on their own? Is there any sign of this kind of adaptive behavior already?
Interestingly, they did find some evidence for this. In Figure 3, left panel, you can see that the models tend to give shorter responses for problems that they can solve, even without that explicit chain of thought prompting. They call those no-caught solvable. So it's like they have some basic ability to tell when a question is easier.
But it's not nearly as good as it could be, right?
Right, there's a lot of room for improvement. Figure 3, right panel, shows that while there's a statistically significant correlation between the token lengths they generate and the estimated token complexities, it's a pretty weak correlation. Table 6 in the appendix backs this up with these low Kendall correlation values. So even for those easier questions, they might still be doing more thinking than they need to. And when they compared the LLMs to a baseline where they just used the same average number of tokens for every question, the LLMs did a little better, but not by much.
So the challenge seems to be in getting the AI to better predict how much cognitive effort, how much token complexity a problem actually requires. How do we move towards this more adaptive, optimal way of doing things?
Well, as a kind of proof of concept, they looked at two different prompt routing strategies. The first one was based on uncertainty. The idea was to use how confident the model was in its initial answer when it didn't do any chain of thought as a signal to decide whether to then ask it to do the longer reasoning. But as you can see in Figure 4, this only led to small improvements.
So the AI's own sense of how unsure it is, it might not be the best guide for whether it actually needs to think harder about the problem.
Exactly. The other strategy they tried was a verifier-based approach. This was a hypothetical situation where they assumed there was this perfect verifier that could tell whether the initial answer without chain of thought was right or wrong. If it was wrong, then the model would be told to do the longer reasoning. And what's interesting is that in Figure 4, this approach showed a much better trade-off, getting closer to that theoretical upper bound we talked about.
That makes sense intuitively. If you know for sure that the first quick answer was wrong, then that's a pretty good sign that you need to think more deeply about it. But of course, in the real world, we don't usually have a perfect verifier just sitting around.
Right. But what this experiment shows is how important it is to have better information about how difficult the problem really is. If we can predict that token complexity more accurately, we can be much smarter about how we use the AI's reasoning power.
So this study isn't just about pointing out where we're falling short, it's also setting the stage for what comes next, right? What did the researchers highlight as the big takeaways for future research?
Absolutely. They emphasize that this whole framework of token complexity, it's a new way to think about and measure the efficiency of LLM reasoning. It gives us a benchmark to compare different methods against. And one of the big next steps is to develop ways to accurately predict that token complexity for any given problem. Then we can use that to create better prompts or even fine-tune the models themselves so that they generate reasoning chains that are closer to that optimal length.
That would be huge, not just for saving money and computing power, but also for making these powerful AI systems more sustainable in the long run.
For sure. Now, they did point out some limitations of the study, like they mainly focused on math problems, so it's not clear if the same things will hold true in other areas. And the way they determined token complexity, it involved generating multiple responses, which is computational expensive. They also noted that their analysis is most relevant for strong models on moderately difficult tasks.
Okay, so let's bring it all together for our listeners. What are the big takeaways from all of this?
The core message is that when it comes to accuracy in AI reasoning, the length of that reasoning process, how many tokens are generated, seems to be more important than the specific way that reasoning is structured. And there's this idea of a fundamental token complexity for each problem, which is the minimum amount of thinking the AI needs to do to get it right. What's really striking is that our current methods for prompting these AI, They're actually pretty inefficient compared to what might be theoretically possible.
So the aha moment here is that these incredibly advanced LLMs might be overthinking things, using way more resources than they need to, and understanding this token complexity is potentially the key to unlocking a whole new level of efficiency and sustainability in AI.
Exactly.
So here's something to chew on. What if we could figure out that token complexity for all sorts of different problems? Could we design AI that's not only smarter, but also dramatically cheaper and more eco-friendly? What would the world look like if we could get even close to the efficiency gains that this research suggests are possible? It's a pretty exciting and maybe a little bit daunting thought.
It definitely is. And if you're really interested in this stuff, you should check out the paper itself. How well do LLMs compress their own chain of thought? A token complexity approach. It's worth thinking about how this whole idea of a required length of thought might apply to other fields where AI is being used to solve complex problems.
Absolutely. It gives us a whole new way to understand how these increasingly powerful technologies work and where they might be headed. Thanks for joining us for this deep dive.